Imagine you're trying to get directions in an unfamiliar city. You stop and ask someone on the street. They point left and say, "Ask at the next corner, they'll know." You walk to the next corner, ask again. That person points back the way you came and says, "Ask back there, they'll know." You walk back. That person points left again. You're going in circles. Neither person actually knows how to reach your destination, but neither of them knows they don't know. Each one is confidently sending you to someone else who they believe has the answer. The answer doesn't exist. You just keep walking. This is almost exactly what a routing loop is. And it happens in real networks more often than you'd expect, not because routers are poorly built, but because of something fundamental about how distributed systems handle incomplete information. To understand how a loop forms, first we need to talk about the gap between when something changes in the network and when every router knows about it. That gap, the convergence window, is where routing loops are born. Let's build a simple example. 3 routers, A, B, and C. Router A is connected to router B. Router B is connected to router C. Router C is the gateway to a destination network. Let's call it network X. Under normal operation, traffic flows cleanly. A sends to B sends to C delivers to network X. Now the link between B and C fails. C is suddenly unreachable from B. B detects the failure and updates its routing table. The direct path to network X through C is gone. B now needs an alternative. It looks at its options and notices that router A is advertising a route to network X. A can reach network X. B concludes, "I'll route through A." But here's the problem. A's route to network X goes through B. A learned about network X from B in the first place. When B told A, "I can reach network X," A added that to its table. A has no idea that B's path to network X just broke. A's table is out of date. It still says, "To reach network X, send to B." So now B thinks A can reach network X and sends packets to A. A thinks B can reach network X and sends packets back to B. The packets bounce between A and B indefinitely, or until something stops them. Neither router is delivering the packets. Neither router knows it's wrong. Each one is faithfully following what its routing table says, and what its routing table says is incorrect. That is a routing loop. The reason this happens specifically in distance vector protocols comes down to what those protocols share with each other. In a distance vector protocol, routers share their conclusions. I can reach network X at a cost of 2. They don't share the full path, or the reasoning behind that conclusion. Neighboring routers accept these announcements and build their own tables from them, without knowing whether the advertising router's path happens to run through them. So when B's direct path to network X broke, and B looked for an alternative, A's advertisement looked like a valid option, because it was when A made the announcement. The advertisement was accurate at the time. It just didn't come with enough information for B to realize it was no longer useful. This problem even has a name: count to infinity. Here's why. After the link between B and C fails, B updates its cost to network X upward, from its previous direct cost to the cost through A plus A's reported cost. B now thinks it can reach network X, just at a higher cost. A hears B's updated cost, recalculates, and updates its own cost upward too. B hears A's new higher cost, recalculates upward again. A hears that, updates upward. Back and forth they go, each one incrementing the cost in response to the other, while packets loop between them. The costs count upward toward infinity, or rather toward a maximum value the protocol defines as unreachable. In RIP, that value is 16. A route with a cost of 16 is considered unreachable and is removed. So the loop eventually terminates, but not until the routers have exchanged updates back and forth 16 times, which takes time, during which packets are looping and nothing is delivered. 16 hops as infinity is a deliberate design constraint. It limits how large a RIP network can be. No valid path should have a cost of 16 or more, specifically so that count to infinity terminates in a bounded time. It's an acknowledgement baked into the protocol's specification that loops will happen and need a ceiling. Link state protocols, like OSPF, handle this far better, and it's worth understanding why, because the difference illustrates something deep about routing design. In a link state protocol, routers don't share conclusions. They share observations, the direct state of their own links and neighbors. Every router collects these observations from every other router and builds a complete map of the network topology independently. When a router computes a path, it's computing it from a full topology map, not from a neighbor's reported distance. This means a loop like the one above simply can't form in the same way. Router A, with a complete topology map, knows exactly which links exist and which don't. It knows that its path to network X runs through B, and it knows that B's link to C has failed because C broadcast that link state observation directly to every router the moment the failure was detected. A doesn't need to receive a second-hand report from B. It got the raw observation from C and computed the consequences itself. When the topology changes, link state routers recompute from first principles. They don't inherit incorrect conclusions from neighbors. They can't be misled by a neighbor's stale advertisement because they're not trusting conclusions. They're trusting raw observations and doing the reasoning themselves. This doesn't mean link state networks are immune to every form of loop. There are edge cases and transient conditions during convergence where even OSPF can produce brief forwarding anomalies. But the structural loop vulnerability that plagues distance vector protocols is largely absent from link state design. Even when protocols are designed to prevent loops, networks add another layer of protection at the packet level because no software system is perfect and packets should never loop indefinitely, even if routing logic fails. That protection is the TTL field, time to live, a number embedded in every IP packet. When a packet is created, it's given a TTL value, typically 64 or 128. Every router that forwards the packet decrements this number by 1. If the TTL reaches 0, the router discards the packet and sends a message back to the source. Your packet was discarded because its TTL expired. The TTL is a countdown to self-destruction. A packet caught in a routing loop gets decremented at every hop. After 64 hops, or however many the TTL was set to, the packet is gone. It doesn't loop forever. It times out. This is why routing loops produce the symptom they produce. Connections that hang rather than error immediately, requests that vanish without response, diagnostic tools that show packets being forwarded but never arriving. The packets are traveling. They're just traveling in circles, losing 1 TTL unit per hop until they expire and disappear. TTL expiration is also the mechanism behind one of the most useful network diagnostic tools ever built, traceroute. Traceroute works by deliberately sending packets with TTL values of 1, 2, 3, and so on. The first packet expires after 1 hop, and the router that discards it sends back a message identifying itself. The second expires after 2 hops, the third after 3. By collecting those expiration messages, traceroute builds a picture of the path packets are taking, hop by hop, to any destination. When packets are looping, traceroute reveals it clearly, the same sequence of router addresses repeating in the output, going in circles. There is one more loop prevention mechanism worth knowing about, and it's one of the most elegantly simple rules in all of networking: split horizon. The idea is straightforward. If router A learned about network X from router B, then A should never advertise network X back to B. Why would it? B already knows about network X. It's the one that told A. Advertising it back would only create the false impression that A has an independent path, when in fact A's path runs through B. Split horizon cuts off the misinformation at the source. In the example we walked through earlier, where B's direct link to C failed and B mistakenly believed A had an alternative path, split horizon would have prevented the loop entirely. A, having learnt about network X from B, would never have advertised it back to B. When B lost its path and looked for alternatives, A's advertisement simply wouldn't exist. B would have no false option to fall back on. It would correctly conclude that network X is unreachable and convergence would happen cleanly. Split horizon is a simple rule. Its impact is significant. It prevents a large class of routing loops in distance vector networks with minimal overhead. Most modern implementations of distance vector protocols apply split horizon by default, which is one reason that the count to infinity problem, while still theoretically present, is far less common in practice than it would otherwise be. Routing loops are, at their core, a story about what happens when distributed systems act on incomplete or inconsistent information. No single router in a network has a perfect, real-time picture of everything happening everywhere. Each one knows its local neighborhood well, and the wider network approximately. When changes happen faster than information spreads, when a link fails before every router has heard about it, there's a window where different routers hold contradictory beliefs. Some know the path is gone, others think it still exists. And in that window, if a router acts on a wrong belief by sending traffic to a neighbor that's also acting on a wrong belief, a loop closes. The mechanisms networks use to prevent and limit loops, link state design, split horizon, TTL countdown, count to infinity bounds, are all answers to the same underlying challenge. They're ways of making routing more robust against the inevitable imperfection of distributed knowledge, ensuring that when the information is wrong, the consequences are bounded, brief, and recoverable. A packet going in circles is the network's version of two people, each thinking the other knows the way. The solution isn't perfect information, that's impossible in a distributed system at scale. The solution is building rules that limit how badly things can go wrong, while the system is catching up with reality.